Okay, so we're looking at the mean value theorem, and the mean value theorem tells us that if we have a function, let's draw a little graph. This is our y-axis. All right, so what we see here is that this red line is the secant line, and its slope, which is the slope of the secant, is actually equal to our average our function f of x average. So I can say f of x, the average f of x, which is the mean, right? The average f of x on the interval from a to b. That's what that slope represents, okay? And there is a value, c, such that, let me draw another line. This blue line that I'm drawing, notice that this blue line is parallel to the red line, okay? And to indicate that, if we have an arrow like this and another arrow on the blue line like that, that indicates that these two lines, the red line and the blue line, are parallel. And the blue line is tangent to the curve at this value, c. So what we have here, this is the c that's between a and b, such that f prime of c, the derivative at x equals c, is equal to the average value of the function from a to b. That is what the mean value theorem means. And we can see that the slope of the blue line is the slope of the tangent line, which happens to be equal to f prime of c, the derivative at c. So that's the mean value, okay? For any function f of x, if that function is smooth and continuous, which means differentiable, on an interval from a to b, there will exist a value c that is between a and b, such that f prime of c, which is the slope of the curve at c, is equal to the slope of the secant line, which is the average value of the function from a to b, and that is the mean value theorem. So now we're going to demonstrate the mean value theorem with a function y is equal to x squared on the interval from 1 to 4. Well, the mean value theorem says the function must be differentiable on the interval. And of course, a quadratic is smooth and continuous. So when x is 1, y is 1, right, because we square 1. And then we have 2, 3. When x is 4, well, y is 16, so this is not going to be to scale, because I'm just trying to sort of draw the picture of what it would look somewhat like, okay? So here's our curve. Imagine here's our parabola. It's curved. Actually quite a bit steeper than that. 16 would be much higher. But anyways, we're looking at the interval from 1, 1 to 4, 16, okay? And we want to find out what is the value between 1 and 4, such that that value, c, that is between 1 and 4, its derivative, f prime of c, is equal to the mean value of the function from 1 to 4, okay? So what we want to do is we want to say, well, what is f prime of x? If f of x is equal to x squared, then f prime of x is equal to 2x, okay? Now let's find the mean value down below. The mean value, of course, is f of 4 minus f of 1 divided by 4 minus 1. Well, f of 4 is 4 squared, and then we have minus 1 squared. 4 minus 1 is 3. So 4 squared is 16 minus 1 over 3, which is 15 over 3. So the mean value is 5, right? In fact, what that means is that if this is our secant line, the slope of the secant line is 5. So we want to find another line such that it's parallel. So imagine that this actually touches. So this black line also has to have a slope of 5. And what we're trying to do is figure out what is this C value. It's a little bit off. Let me fix that. I think our C would be a little, maybe come down, maybe closer to here someplace. What is that C value? Well, what we want to do is, in order for this to be true, then f prime of C must equal the mean value 5, right? In other words, 2x has to equal 5, because we're trying to find that x value, which this is true. Divide by 2, we have x is 5 over 2, which of course, oops, that's a 2. Let's fix that. So x is 5 over 2, which is 2.5, right? So that's our C value there. Our C value is 2.5, because when C is 2.5, f prime, this is 2.5, f prime of 2.5 is 5. So we are demonstrating the mean value theorem here because we're saying that, first of all, the function x squared is differentiable on the interval from 1 to 4. We found the mean value from 1 to 4, it's 5. We found the derivative of f of x, it's 2x. And we said, well, when is this derivative 2x equal to the average value 5? So here's a little bit of algebra, and we said when x is equal to 2.5. So here we've demonstrated the mean value theorem for the function y equals x squared on the interval from 1 to 4. So here we're looking at Rolle's theorem, and Rolle's theorem is the same as the mean value theorem, except the stipulation is that this is when the average value is 0. Okay, so here we have Rolle's theorem, and Rolle's theorem is the same thing as the mean value theorem with an additional caveat, and that is that the mean value is 0, okay? So let's draw a picture of this. So here's my y-axis and my x-axis. And so what we're saying with the mean value theorem is if a function f of x on an interval from a to b, so here's our interval is a to b. Okay. If there is some function height f of a, and then there's another function, the height at b is the same. That is to say that f of b is equal to f of a. Then these are our starting and ending points of our function, our curve. So I'm going to go ahead and draw the curve. Now the curve doesn't have to be a straight line. Here's my curve. All right? Now my curve could sort of continue. But we're only looking at it, and so maybe it does continue, but we're only looking at this curve on the closed interval from a to b. So now I'm going to draw the secant line, and the secant line looks like this. This is our secant, right? And the slope of the secant is 0, right? And the slope of the secant is 0, that is the mean value, right? The mean value is is f of b minus f of a over b minus a, and b minus a is going to have some value because we can see that there's a distance between a and b. But a minus b is 0. So if the numerator is 0, the value is 0. So the average value is 0, and now what we're saying then is that there is a value c such that f prime of c is also equal to 0. And sure there is, because if I draw my secant lines, I guess I'll do my tangent lines to the curve. Imagine this is touching. Here's a tangent line, tangent to the curve with a slope of 0. And here's another tangent line, tangent to the curve with a slope of 0. And here are the points of tangency, right? And so, in fact, there is more than one c value. Here's c1, and here's a point of tangency at x equals c2, right? And that's to say that f prime at c1 is equal to 0. And here, f prime at c2, we've got two c values, is also equal to 0. So Rolle's theorem says that there is a value c that's between a and b, and it can also be equal to its endpoints as well, such that f prime of c is equal to 0, and that is when, in fact, initially we know that the height at the beginning, f of a, is equal to the height at the end, f of b. In other words, the average value is 0. So that's Rolle's theorem. So the intermediate value theorem says that if we have a function f of x, and the f of x is smooth and continuous on an interval from a to b, then, if this is true, then there exists a value c that is between a and b, and it could be on an endpoint as well, such that f of c is between f of a and f of b. So here's our f of c, and it could be equal to either f of a or f of b, but it's in the interval, it's somewhere in the interval between f of a and f of b, okay? So this c is between the starting and ending height of the function, and c is between the domain from a to b, okay? So let's draw a picture of that. Here's my y-axis, here's my x-axis, and I'm going to go from a to b, and I'll draw a blue curve, and let's just say our blue curve, maybe it does this, but it's smooth and continuous. And a has a height, f of a, and when x equals b, we have a height, it's a freehand here, f of b. And so we're saying there is a value c such that f of c is between f of a and f of b. So there's actually more than one, but there's at least one. So here we go. Here's our value c. And clearly we can see that f of c is between f of a and f of b. And that is the intermediate value theorem.